Module 2, Lesson 7, Interpolation. For this lesson, we'll be covering the curve-fitting techniques known as interpolation. We will then discuss the first interpolating technique, which is known as the Lagrange interpolating polynomial, and how to determine an nth-order Lagrange function, and some sample problems to apply this given technique. Interpolation is the most common method to estimate intermediate values between precise data points. The common method used for this purpose is called polynomial interpolation. It's a basic curve-fitting technique whereby the data points eventually are used and the model function, which is your nth-order polynomial given by this form, passes directly on each data point on your given data set. So for n plus 1 data points, there's only one polynomial of order n that passes through all the data points. The polynomial interpolation consists of determining a unique nth-order polynomial that fits your n plus 1 data points. Although there is one nth-order polynomial that fits your n plus 1 data points, there is a variety of mathematical formats in which this polynomial can be expressed. If there are two data points, then that would mean a linear interpolation. If there are three data points, then that would mean a quadratic interpolation. If you have four data points, then that would mean a cubic interpolation. The Lagrange interpolating polynomial function is simply a reformation of your Newton's polynomial function that avoids the computation of divided differences. Note that all interpolating techniques come from or was derived from Newton's interpolating polynomial function. Thus, the Lagrange can be represented concisely as this given particular summation formula, which is equivalent to the product of your Lagrange term multiplied by your function fxi. Each corresponding function value depicted on your given set of data points is then multiplied to a Lagrange function, and their product is simply summed up. How do we then establish this Lagrange Li of x? The formula for your Lagrange Li of x is simply equivalent this time to the pi of x minus x subscript j divided by x subscript I minus x subscript j. When you see the symbol pi, this implies a continuous product. When you see the symbol sigma, it implies a continuous summation. Therefore, I continuously multiply the following terms on my numerator, which should mean subtracting x with other values of x that are seen as my data points, other than, of course, my xi. And your denominator would be the xi value divided by a minus the other values of x, other than, of course, xi. Because if I subtract xi with xi, I would eventually end up with a zero term, thus giving me an undefined function value. Therefore, the linear version of this technique would simply be connecting two data points, x0 and x1, along with its function fx0 and fx1. We then evaluate for its Lagrange term, which is called L0 of x and L1 of x. After which we multiply them to your function, which should give us this particular lines. And then when you sum them up, they produce a unique straight line that will connect the two data points noted on your given data set. Therefore, the linear version of your respective Lagrange term would be the summation of all the products designated by the Lagrange term, which eventually, when multiplied to your function, creates a unique nth order polynomial function that passes through all your data points. Hence, the first order linear interpolation would comprise fitting the data points x0, fx0, and x1 with fx1. Therefore, your first order or linear function would simply comprise of the product of the Lagrange term L0 of x multiplied to fx0 plus L1 of x multiplied to your fx1. Since there are two functions, namely on your data point, fx0 and fx1, therefore you end up with two Lagrange terms multiplied to each of your given function, L0 of x for fx0 and L1 of x for fx1. In order then to determine this Lagrange term, your L0 of x is simply x minus all other values of x except x0. Note that the only other value of x on your given data set is x1. So that would mean your numerator would be x minus x1 only. And on your denominator, you will have the data set x0 minus other values of x other than x0. And the only other value of x other than x0 would be x1. Therefore, your denominator would simply be x0 minus x1. This Lagrange term is then multiplied to your function fx0. Likewise, your L1 of x is evaluated to be, its numerator to be x minus other values of x except x1, which in this case would only mean x0. Thus, your numerator would be x minus x0 divided by the data point x1 minus the other values of x, in which case the only other value of x other than x1 would be x0. Thus, you end up with a difference of x1 minus x0, and then multiply that given L1 of x with your function fx1. Upon doing so, you will notice that each Lagrange term is a linear function. And then the process of simplification is simply applied in order to derive the linear function. For a second order interpolation, then, we require three data points. You have x0, fx0, you have x1, fx1, and x2 with fx2. Hence, your second order Lagrange interpolating function would simply be the product of L0 of x multiplied with fx0 plus L1 of x multiplied with fx1 plus L2 of x multiplied with fx2. Note that there are now three Lagrange terms since there are three functions depicted on your given set of data, fx0, fx1, and fx2. How do we evaluate this time L0 of x? L0 of x would now be evaluated to be its numerator as x minus other values of x except x0. Note that there are now two other values of x except x0, which should imply that your numerator would be a continuous product of x minus x1 multiplied with x minus x2. Note that if you simplify these particular terms, you'd end up with a quadratic function bearing x squared. And when you divide it, it becomes the data point itself, which is x0, minus the other values of x. And again, you end up with two other values of x. Therefore, you'd end up with a continuous product of x0 minus x1 multiplied with x0 minus x2. And this Lagrange term L0 of x is multiplied to your fx0. Likewise, we do the same for L1 of x. L1 of x would contain a numerator equal to x minus other values of x except x1. Therefore, you'd end up with a product of x minus x0 multiplied with x minus x2 divided by the data point itself, which is x1, minus the other values of x, which should mean, again, a continuous product of x1 minus x0 multiplied with x1 minus x2. This now is L1 of x multiplied to your function fx1. And finally, in order to determine your L2 of x, that would mean x minus other values of x except x2. So that would mean a continuous product of x minus x0 multiplied with x minus x1. Thus, for your denominator, you would have the data point x2 minus x0 multiplied with x2 minus x1, giving you as your L2 of x, multiplied to your function fx2. Note that each Lagrange term on this given particular function is a second order function. This is the illustration for a second order quadratic function. Note that each Lagrange term there is represented as a blue curve, which shows you that each Lagrange term is a quadratic function. And when these quadratic functions are eventually summed up, they form your general second order function or quadratic function f2 of x. For a third order interpolation then, or a cubic interpolation using Lagrange, you end up with 4 data points now, noted to be x0, fx0, x1 and fx1, x2 with fx2, and x3 with your function fx3. To evaluate then your third order or cubic function, always remember that each of these functions is multiplied by their respective Lagrange term and their products summed up. So your fx0 is multiplied to L0 of x, your fx1 is multiplied to your L1 of x, your L2 of x is multiplied to your function L2 of x, and your x3 function fx3 is multiplied to your function L3 of x, giving us a formula for your L0 x now to be equivalent to x minus x1 multiplied to x minus x2 multiplied to x minus x3 divided by the data point itself, which is x0 minus x1 times x0 minus x2 times x0 minus x3, making up your L0 of x multiplied to your fx0. Likewise, we do the same for L1 of x, varying our given function, as well as L2 of x and L3 of x. Note that you could easily generate here the respective Lagrange term for each of the respective function given on your data set. However, the difficult part under Lagrange interpolation is simplifying your given function. Note that each Lagrange term here is a cubic function. Let's try to evaluate an example using Lagrange interpolating polynomial. Let's say I wanted to fit this given set of data using Lagrange interpolation. Since there are 4 data points, therefore we expect that we end up with a cubic polynomial function. Hence, I will then label your respective data values, x0 being 1, therefore your fx0 would be -4, your x1 would be 4, therefore your fx1 would be 59, and so on and so forth. Therefore, we expect a third order Lagrange interpolating polynomial function with a expanded version of your cubic function to be L0 of x multiplied with fx0, L1 of x multiplied with fx1, L2 of x multiplied with fx2, and L3 of x multiplied with fx3. So when we evaluate for your given function, the expanded version of your Lagrange term L0 of x would simply mean this term, which is x minus x1 times x minus x2 times x minus x3 all over x0 minus x1 times x0 minus x2 times x0 minus x3, multiplied to your fx0. As derived from our previous slide, the values for your L1 of x would simply be like this. The value for your L2 of x and the value for your L3 of x multiplied to their respective function would be given off by this expanded formula. When we substitute then the given values, we end up now with this solution. Note that your respective denominators on your given particular Lagrange terms are all numeric values. Therefore, you could simplify that and multiply that by your function value. Whereas the numerators will all be polynomial functions that are in the third order. When simplifying each Lagrange term, then we would end up with an L0 of x fx0 to be equivalent to -1/6 multiplied to x cubed minus 4x squared minus 9x plus 36. Your simplified L1 of x multiplied to fx1 would simply indicate 59/21 multiplied by x cubed minus x squared minus 9x plus 9. Your simplified L2 of x multiplied to fx2 would simply mean 4/21 multiplied with x cubed minus 8x squared plus 19x minus 12. And your simplified L3 of x fx3 is equivalent to -11/6 multiplied to x cubed minus 2x squared minus 11x plus 12. When evaluating each of these Lagrange terms, you would end up now with a simplified coefficient for your x cubed to be -1/6 plus 59/21 plus 4/21 minus 11/6, and then multiply to your x cubed. You'd end up with a simplified coefficient for your x squared now to be 4/6 minus 59/21 minus 32/21 plus 22/6 multiplied to x squared. You'd end up with a simplified coefficient for your x now to be 9/6 minus 531/21 plus 76/21 plus 121/6. And you'd end up with a constant of -36/6 plus 531/21 minus 48/21 minus 132/6. When you simplify then the coefficient of x cubed, you'd end up with a value of 1. When we simplify the coefficient of x squared, we end up with a value of 0. When we simplify the coefficient of x, we end up with a value of 0. And when we simplify our constant, we end up with a -5. Therefore, your cubic function, when simplified, is simply x cubed minus 5, which eventually shows a perfect fit model function onto your given data set, such that when we substitute the value of x there on your given data set, your given respective function will then reflect as based from this given perfect fit model cubic function. This ends Module 2, Lesson 7.